All right, this is Open Up Resources, Unit 1, Lesson 10, Composing Figures, recorded live with 5th period. To get started today, I've asked students to trace on tracing paper this triangle, triangle ABC. What we're going to be doing, as it says in this lesson, we're going to find measurements without actually having to measure based on the things that we already know about rigid transformations. So to get started, we are going to reflect triangle ABC over line AB. Those of you who already have it traced, you guys should be able to do that successfully. I will be modeling for online students what that is going to look like for them. We have triangle ABC on tracing paper. A reflection over line AB means that I am going to be flipping this tracing paper. So I'm physically flipping it. That is what a reflection looks like. And then to make sure I flipped it correctly, I'm making sure that AB is lined back up with AB. And then, since we need this figure to be on our paper below, that means that I need to poke those holes through and get those points drawn in there, so that when I move the tracing paper, I'm still going to know exactly where that triangle is going to be. So get that traced into place in its new position. That is how I would do that with tracing paper. And now you guys are already familiar with this. You know that this is not geometry software, so it doesn't always work the same way. But since you saw me do it for real, you understand that this is the position that that figure is now in. And now that it is in that position, we're going to label, as it says, label the image of C as C prime. So this is C. When I reflected C, it is now in this position, and we're going to call that C prime. A few things to observe here. When I reflected this triangle, did the point A, did that change position? No. So I don't need to relabel it A prime because A is still in the same place as it was before. Same thing with B. B is in the same place as it was before, so I don't need to relabel that B prime. We're just going to keep it as is. And now we're ready for the next piece. Again, I'm going to kind of switch over and model it with tracing paper, and then I'll have to switch back over here to kind of show what that looks like. It says rotate triangle A, B, C prime around A so that C prime matches up with B. So this is what that's going to look like. You can see in my tracing paper, I have flipped it. And I'm just going to relabel this point on my tracing paper. I'm going to call it C prime as well. And now I'm rotating around point A. So I've poked my hole through the tracing paper, and I'm going to spin it around so that that C prime lines up with B. I'll show that one more time. This is once it was flipped over and reflected. Now I've poked my hole through A. I'm going to be rotating C prime, that's the new point here, so that it lines up with B. Now there's nothing to draw because you can see that that is already the same triangle as we had before, so there is nothing to redraw. So what is the purpose of this whole lesson? And it is this. I can then take this reflected triangle, and I can, let me lock this one in place so it doesn't move. I can now rotate it back into position so that that C prime lines up perfectly with B. And the point of that is now we have proved that angle C is the same as angle C prime. I'm going to write that down because that's important. Angle C is the same as C prime. And when I did that rotation and got that C prime back into position here, I hope that that also shows the angle C prime. Remember, C prime is the same as C. That's what we just wrote down, angle C, which is the same as C. is also the same as B. So again, that kind of expresses and models what we're trying to show up here, finding measurements without actually measuring. I don't have to measure and use a protractor to know that C and B are the same when I can use those rigid transformations to prove that. And so that kind of leads us into something that's going to come up again later. It says angles of an isosceles triangle. Just a quick review from previous grades. An isosceles triangle is a triangle with two sides the same length, which you can see in that image. We have two sides that have the length of 3, but we also were able to show that it's a triangle with two angles the same as well. Again, we were able to show that C was the same as C prime, which was the same as B. So we know that C and B have the same angle measure. The next one for our in-class students, we are going to be using our calculators. Now, students who are learning online, you don't have an applet for this. You can either observe and see what we do in the calculators, or you can do this physically with your tracing paper and finding the midpoint, etc. For you in-person students, this is what it looks like. We're going to create a new document. And just like we've done in the past, our new document is going to be a geometry page. So in this new geometry page, I want you, now before you do anything, listen to all of the directions. I want you to create a triangle that looks like this triangle, but notice a few things, okay? Again, you're not doing anything yet, you're just listening. Do you see how this is labeled A and then B and then C with A at the top? Now what comes first in the alphabet, A, B, or C? A. Okay, and we have now set up the calculators with a certain feature. And so I want, before we draw the triangle, I want you to confirm that this is set up. And for those of you who don't have it set up, you're going to fix that right now. We're going to go menu, option 9 settings. So you guys are all doing this with me. And if you scroll down to the very bottom, the very last option is automatically label points. Now, we don't always want it to do this, but for right now, I like that the calculator will do this. Make sure that that is checked. If it's checked, just hit OK. You can even hit cancel if it was already checked. If it's not checked, then please check it and save that setting. And so what that means is as I create a triangle, and again, now I want you guys to just watch, you're not doing. As I create a triangle, when I create that triangle, do you see how it automatically labeled it? And do you see where it placed the points? The first place that I clicked was that first letter. Now it's going to continue. The first place that I click is the first letter, then the second letter B, then the next letter C. So with that in mind, as I am trying to create a triangle with A up on the top, B on the left, and C straight across on the right, make sure that you are clicking in the correct order. And again, I will demonstrate that for you. A needs to be up here, B off to the left, and C straight across. Okay, now you do it. That's going to be menu, shapes, triangle, A up at the top, B off to the left, and C straight across. I don't want it huge. I want it to be about the same size that mine is. So notice how much extra blank and white space I have around on the outsides. You guys should have about that same amount. Again, the whole point is we're trying to make it look like this image that you have on your paper, okay? So notice that this is going straight across. Notice the angles, try and match them. It's not going to be perfect, but I want you to try and make that same image. And if you don't like where some of your points ended up, you can always change it to make it match a little bit better. So go ahead and make that happen now. Okay, I see that almost everybody is ready to go. Here's the next thing that we're going to do. When we return to our packet and read, it says draw midpoint M of side AC. Again, watch to see what I do first, and then you guys can do it on your calculator. We're going to use the calculator to find the midpoint. And so what I'm going to do, again, I'm showing first, you guys are watching first. Menu, construction, midpoint. And then all you have to do is just click on the side and it will place that midpoint. Do you see how I'm hovering and it already shows me where that midpoint is? And here I can hover and it will show the midpoint, and here I can hover and it will show the midpoint. We just want the midpoint here. Now it did not automatically label that point. That's okay. It's not going to be a major deal that that's not labeled, but now I want you to do that. I'm going to Control Z, and you guys are all going to do this with me together. That's menu, construction, midpoint, and then we're going to click on that side, and it will place that midpoint for us. Okay, looks like almost everybody's where they should be. The next step, it says, now that we've drawn midpoint M on side AC, rotate triangle ABC 180 degrees using center M, that would be that midpoint that we just drew, to form triangle, which we're going to call CDA. So this triangle is going to be called CDA. Our calculator is automatically going to label it something different, and that's okay. We'll be able to fix it. So again, watching first. We've done these rotations in our calculator before, but watch first. Menu, transformation, rotation. Remember, we're just watching. And the directions say first click the object, then the rotation point, then we'll enter the rotation angle. So here's the triangle. I'm rotating it around this point. And as soon as I click saying this is the point, that's also when I'm going to type in 180 degrees. Press enter, and it will rotate it for you. Okay? So again, I'm going to Control Z so that I can do that with you. Now you guys are going to do that with me. We'll do it all together. I do see a couple students who still don't have that midpoint. You will not be successful with this rotation if you do not have that midpoint on your screen. Menu, transformation, rotation. Thank you for doing this with me. First, we click on the triangle, then we click on the midpoint. Then, as soon as I click on that midpoint, that's when I can type in 180 degrees and enter. You can see many of you have been successful with this. Calculator automatically labeled, so you're going to notice that this was originally A, but when it was rotated, they're calling it C prime. And that's okay because it helps us keep track of what angle is what now. This was originally C, but you can see that when it was rotated, it's actually A that is now over here, okay? So I'm going to keep both of them just so that we can kind of keep track of angle A is now rotated over here, and this is angle A. I am going to fix this one, though. It is B prime. But I also want to add an extra label, and so I'm gonna see. Can I do this? Can I call it point D? No, it's not gonna let me change it. So I have to double click on this. I'm hovering over where it says label right now. If I double click, then it creates that text box so that I can call it D. So change that B prime so that it's D. Again, here's those directions. Oh, it's not gonna Control Z that. Hover to where it says label, double click, and then type in the text box so that that is relabeled point D. Because I pressed shift and then the letter. That's how I get things capitalized on a computer the same way as in a calculator. Now I have that image in my calculator, and you can see exactly how we created it, and it allows us now to discuss and answer the question that we see back on our paper, what kind of quadrilateral is this? Specifically, what is A, B, C, D? That's why we call this D. A, B, C, D. What kind of quadrilateral is this? Quickly discuss with your groups. How do you know what kind of quadrilateral it is? What is it and how do you know? 30 seconds, go. I better not be hearing rhombus. No. These are very obviously different lengths of sides. I definitely should not be hearing rhombus. I definitely should not be hearing rectangle because these obviously do not have 90-degree angles. And your time is up. What is the name of this figure? Audrey. It is a parallelogram. Yikes, 8th graders, you need to go back and review 4th grade shape names, I think. Parallelogram. Now, some things to review. Obviously, we need to go over them. Why is this not a rhombus? Well, obviously, this side length is very different than this side length. As we mentioned yesterday, rhombus doesn't mean diamondy shaped or slanty. That's not what rhombus means. Rhombus means all sides the same length. It is clear these are different side lengths. So we couldn't even have rhombus come up in our brains. It is definitely, obviously not a rectangle because rectangles have all angles 90 degrees. And those are very, very obviously not 90 degrees. So rectangle shouldn't have even popped up into our head. Parallelogram has the feature, and I'm reviewing right now, you guys should be writing down, parallelogram has the feature that opposite sides are parallel. We're writing this down because obviously we need to review this. Opposite sides are parallel. You could also define it as two pairs of parallel sides. Either way, this figure fits that description. Two pairs of parallel sides, or opposite sides parallel. Now that we've reviewed what a parallelogram is, I need you to think back to our previous lesson, parallel moves. When I have a line, or in this case, a line segment, and I rotate it 180 degrees, it either becomes the same line if I rotated around a point there, or it would become a line parallel. Rotated 180 degrees would become a line parallel. And same thing if I'm looking at AB, rotated 180 degrees would become a line parallel, which we now call CD. So we need to make sure that we write that justification as well. We know it's a parallelogram because, we're writing this down, line segments rotated 180 degrees I'm not going to say become, I'm going to say are parallel to the original line. We observed that yesterday. That was one of the key things that we highlighted. And now we're ready for our next exercise. I am going to continue to use the calculator to show you something. I don't want you guys to continue to use the calculator. But what I want you to do is turn to the next page where you see this figure. And I hope that this figure looks somewhat familiar because it's one that we almost created in our calculator. Do you see what we created in our calculator? Oh, yeah. Do you see it right here? Okay. So you should be able to answer question 1. Okay. Going back, it says the picture shows 3 triangles. Triangle 2 and triangle 3 are images of triangle 1 under rigid transformations. Remember that term rigid transformations means we're keeping the side lengths and we're keeping the angle measures, that nothing is changing. So how did we change triangle 1 to be triangle 2 in our calculator activity? What did we just do? Talk with your groups and write it down. Now share your answer with me since you had a chance to check in with your groups. How did we take triangle 1 to triangle 2? Good, I love this number of hands. Lucas?
We found the middle point of triangle 1 between A and C.
Good, we found that midpoint.
And then rotated the triangle 180 degrees, right?
Yes, exactly. We rotated triangle 1. So we're writing this down now that we've talked about it. Rotate triangle 1 180 degrees around the midpoint of AC. With that in mind, how do you think we take triangle 1 and turn it into triangle 3? Quick discussion at your tables first before we come back together and answer. Discuss now, how are we going to take triangle 1 and turn it into triangle 3? Okay, and what do you think? You've had your chance to discuss. Zeta? It is not a reflection. You have to be really careful. I had my last class making some mistakes like that too. Take a look and see. Do you see right here, line BC? If it's staring straight into the mirror, and this is that mirror line, then I need to be staring straight into it. Okay, which means that it should be going straight back, and each one of these points would have to be going straight into that mirror, and it's getting really hard for me to try and draw that and model it. My angles are not turning out quite so right. That point would have to be all the way over here, and it's not. So it's definitely not a reflection. What would it be, Callista? Exactly. Find the midpoint of AB and rotate it 180 degrees around that midpoint. So let's write that down and then I'll show you in the calculator. Rotate triangle 1. We are all writing this down. All pencils are moving. Rotate triangle 1 180 degrees around the midpoint of AB. And again, I will model this in the calculator. I don't want you guys to. Just trust me. So I'm going to go menu, construct, and I'm going to construct that midpoint. Now I have a point to rotate it around. Menu, transformation, rotation, rotating this triangle around this point 180 degrees. And you can see that is the exact image that we have on our paper, okay? And the reason why that is important to recognize those rotations is, again, I want to start comparing side lengths and angle measures without actually having to measure them. So I'm going to get you started, and I'm going to show you that, do you see when we rotated AB, how it became this line here, CD? Look at that again, AB, do you see AB?
Yeah.
When it's rotated, it becomes CD. So that means I know, without even measuring, that AB, remember our shorthand, is congruent to, or is the same length as, AB is the same length as CD. And how do I know that? Well, because CD is AB, just rotated. AB is congruent to CD because CD is the image of AB after a rotation. You can especially see that, and I'll return to the screen in just a second, you can especially see that in the calculator, because in our calculator, Do you see how AB, this point was relabeled A prime? And originally that was labeled B prime until we relabeled it D. So that is proof that AB is the same as A prime B prime, or in other words, AD or CD. And so that's how we know that they are the same lengths. Without us having to measure, we know they're the same lengths. Can you find other side lengths that are the same? Find at least one more pair of side lengths that are the same. Make sure you're able to explain how you know. Discuss with your group. I'm only giving 15 seconds because it's just that easy. 15 seconds, go. Okay, I just need one person to share something that they discovered, something that they found is the same length. I'm going to go ahead and color code, and since I did AB in red, I'm going to highlight AB in red and show that it's the same as CD. Okay, Nadia. Yes, and as you mentioned that, I'm going to be really particular on which order we're talking about them, okay? So BE. Look at where we start with BE. B starts here, and it goes along that long diagonal to E. Okay, so BE. Now, what point corresponds with B? It would be A. So instead of calling it CA, I would actually want to call it AC. But you've got the right idea. You're naming the right segment. I just want to be really, really precise in how we talk about that. BE and AC. BE is congruent to AC, and again, we can say the same thing because BE is the image of AC after a transformation, after a rotation specifically. And now it gets to be tricky when we start looking at the angles and how we're going to talk about those angles. So again, I'll help you out with the first one, and then I want you guys to do the second one on your own. It says find two pairs of angles in the diagram that have the same measure. So I'm going to choose angle ABC, which means I would start at A, go to B, and go to C. And look at the angle that I traced. Do you see that angle? I'm actually going to color it in. What other angle has the same measure? And I'm going to use that shorthand again. Angle A to B to C. I've colored purple. Look at triangle 2. Should we go to triangle 2? Which angle would that be? Maybe you can see it. Maybe you don't know what to call it. We'll be really careful with that. A, B, C. Xander, what do you think? Yeah, and you said it in the correct order too. C to D to A. That's the angle that I traced out. So I'm going to just color that in so it makes it easier to look at. C to D to A. Angle C, D, A. And again, we can say the same thing. We know that because angle CDA is the image of angle ABC after rotation. And I would love to continue, but for the sake of time, I'm going to skip. I'm going to leave it to you guys to see if you can find another angle, but I'm going to move on. It's time to summarize. Highlighting the key pieces of information that I hope you learned today. Earlier, meaning in previous lessons, we learned that if we apply a sequence of rigid transformations to a figure, then corresponding sides have equal lengths and corresponding angles have equal measure. So that's not anything new. However, this is the part that's new. These facts let us figure out things without actually having to measure them. We can figure out how long sides are without actually having to measure. We can figure out angles without actually having to measure. We start with this example, ABC, triangle ABC. You can see angle A is 36 degrees. So when I reflect triangle ABC across AC, you can see that this angle is also going to be 36 degrees, right? We are able to do this without actually measuring, just knowing that rigid transformations are going to keep those angle measures. And that's all that it says here. It just summarizes all of that. So I'm not going to read word for word through all of that. I am going to say when we construct figures using copies of a figure made with rigid transformations, we know the measures of the images and of the segments and angles. They're going to be equal to the original. That is more important than you realize. That is going to be really helpful in our coming lessons. And now we're going to finish up with our cool down. This takes extra brain power, so make sure your brains are on. Here we have a diagram of ABC, triangle ABC, and triangle ABC. And I'm going to read so we can really make sense of this. It says, on the left side, triangle ABC has been reflected. Think about what those reflections will look like. This is a reflection. And on the right side of the diagram, triangle ABC has been rotated. This is a rotation. Look at how similar they are, but they are different. So, are your brains working? Let's start with this. If angle B is 64.3 degrees, what do we know about angle B? 64.3 degrees. That's the easy part. Now, if this line segment is 2.7, where is the reflection of that image? Remember, when we look at reflections, we look straight into that mirror, and our reflection is looking straight back out. So if this is 2.7, is this the segment that's 2.7? No. Yes? No. I hope you're saying no. My last class said yes. That one's the 2.7. And if this segment is 3.2, remember this segment is staring straight into the mirror, so its reflection is staring straight back out. So which segment is the 3.2? The CD. And we're labeling that. And now rotation. Twist it in your mind now, just like a rotation is a twist. If this is 2.7 and now we're rotating around M, where is this 2.7 going to be? What is the name of it? Callista. It is CE. This is the 2.7 because we are going around. That's a rotation. And this one is 3.2. So where is it in the new figure? On the top. Yep, 3.2. And of course the angle 64.3, and this one is going to be 64.3 because this angle was also rotated into that position. That is it for lesson 10. You do have homework. These practice problems, lesson 10, that is your homework. Have a great day, and we'll see you next time.